Hello, we are a group of university students passionate about engineering, chemistry, and biology, and this is our solution to the nuclear waste storage contamination problem. Nuclear waste storage is a critical issue, particularly since more than 31 countries depend on nuclear energy. Although nuclear energy generates low greenhouse gas emission, it carries serious problems. Our goal is to tackle the harmful effects of nuclear waste, particularly at the Hanford nuclear site in Washington. The Hanford site was established during World War II to produce plutonium for nuclear weapons, including the bomb dropped on Nagasaki on August 6, 1945. Manufacturing ended in 1989, but high-level waste remains stored in underground tanks. Many of these tanks have leaked, contaminating underground water and the Columbia River. Some common contaminants are uranium and strontium-90. As of 2019, the site holds 56 million gallons of radioactive waste, with one tank leaking up to 300 gallons annually, according to Governor Inslee. Nearby residents face alarming high cancer rates, particularly amongst Native American communities that depend on the river and salmon fishing for their cultural heritage. Downwind communities are also endangered by harmful airborne contaminants, highlighting a public health concern. The current solution to this problem include injecting the phosphate mineral apatite into the aquifer, as it traps and separates strontium-90 from the underground water. However, this method does not solve issues like diverse contaminants, large plump size, cost and time constraints, deep contamination, complex geological forms.
To decontaminate the soil and groundwater in Hanford, we propose to use injection sites to inject a mixture containing apatite and microorganisms. After the injection sites, there will also be a barrier with the same mixture that the contaminated groundwater has to flow through to reach the Columbia River to ensure a more proper decontamination. The microorganism mixture will contain the microalgae Scindesmus spinosus and Clostridium maliniferum, to name a few. After more research into different microorganisms that remove the other toxic chemicals in the nuclear waste, we will add them to the mixture. The microalgae Scindesmus and Clostridium are able to remove strontium-90 from the environment they are in. MicroRem solution diagram. This is our diagram. The red dots are the strontium-90, one of the dangerous chemicals we're leaking into the ground. The microorganisms in apatite will remove the strontium and dangerous chemicals in the injection sites and the barrier. Apatite is currently used to trap strontium. However, it is limited and costly, which is why we're going to use a combination of the microorganisms and apatite. MicroRem will decontaminate the groundwater and soil, minimizing the impact the harmful toxins have on the environment, health, and safety of Hanford and the residents. As a result of removing the nuclear contamination, the environment of the Columbia River will not be threatened. MicroRem is innovative because we're applying in situ bioremediation to the nuclear industry. We are combining methods in place currently and from different industries to apply into nuclear industry. Bioremediation in nuclear decontamination is a more cost-effective and environmentally friendly alternative to current methods in place.
In order to contain the microorganisms as well as to contain contaminated water and prevent fresh water from entering the area, there will be a barrier consisting of one of the most abundant materials on Earth, silica. The crystal lattice structure of silica will allow for the containment of the coagulated apatite with contaminated water, ensuring the water molecules are too large to permeate through to the fresh groundwater. Our next key steps will include reaching out to professors who specialize in nuclear power, quantum physics, and biological processes in order to try and consolidate our ideas and bring them to reality. Our team will design the mixture components and research the environmental and economic impacts of this solution. We will also create a 2D drawing of the system. Our team will also utilize AI models to predict the rates at which our microalgae can reduce the half-life of strontium-90 as there are many relevant studies of bioremediation using microorganisms that can serve as the basis of our prototype. This will feasibly allow us to create a model system that will hopefully be able to protect future generations from the fallout of radioactive effects. We appreciate you taking the time to listen to our pitch. Thank you.